Let's look at different types of polar equations. On the Cartesian grid, when we graph the equation y equals x squared, we get a parabola. Similarly, if we graph the equation x squared plus y squared equals 4, we get a circle. However, on a polar grid, when we graph certain equations, we get a number of different kinds of shapes. Some of these shapes are cardioids, limaçons, lemniscates, and spirals. Right now, we're going to focus on cardioids. There are two different forms that we can graph when dealing with cardioids. The first form is r equals a plus or minus b sine theta. The other form we use is r equals a plus or minus b cosine theta. If you were to plot either of these equations on a polar grid, the graph will be a cardioid if a is greater than 0, b is greater than 0, and a over b is equal to 1. The word cardioid may sound familiar. Your cardiovascular system pumps blood throughout your body, and a cardioid is roughly heart-shaped. This cardioid is the graph of the equation r equals a minus b sine theta. The graph of r equals a plus b sine theta is the reflection of the cardioid across the polar axis. Notice that both of these graphs are symmetric about the line r equals pi over 2, which is the vertical line in the picture. If we replace sine with cosine, the equation becomes r equals a plus b cosine theta. Notice that the graph is now symmetric about the polar axis, or the horizontal line in the picture. Finally, if we change the addition to subtraction, we end up with the equation r equals a minus b cosine theta, and a cardioid that has been reflected across the vertical line r equals pi over 2. Now that we have seen what a cardioid is, let's look at how to graph one. The first step is to check the equation for symmetry. Remember, cardioids are either symmetric about the vertical line r equals pi over 2 or the horizontal polar axis. Next, set r equal to 0 and solve to find the corresponding values of theta. Now we can use what we know about sine and cosine to find the maximum value that r can be. To do this, we can create a table using these values. If you don't have enough points, find r for additional values of theta. Try to pick thetas so that the point will be fairly easy to plot. Consider the way the sine and cosine functions behave when trying to choose values of theta. Points like pi over 2 or 3 pi over 4 may be useful additional points. Finally, plot the points and sketch the graph. Let's graph r equals negative 4 cosine theta plus 4. First, we'll check for symmetry. We saw above that a cardioid is either symmetric about the line r equals pi over 2 or about the polar axis. Let's check for symmetry about the polar axis first. Recall that an equation is symmetric about the polar axis if we can replace theta with negative theta in the equation and get an equation that is equivalent to the original equation. Replacing theta with negative theta gives the equation r equals negative 4 cosine negative theta plus 4. Remember that cosine is an even function, so the cosine of negative theta equals the cosine of theta. Replacing cosine negative theta with cosine theta gives our original equation r equals negative 4 cosine theta plus 4. Therefore, this cardioid passes the test and is symmetric about the polar axis. Our next step is finding the zeros of the equation. To do this, set r equal to 0 and solve for theta. To solve, 0 equals negative 4 cosine theta plus 4. Add 4 cosine theta to both sides of the equation. Now we have 4 cosine theta equals 4. Divide both sides by 4 to get cosine theta equals 1. Remember that the cosine of 0 is 1, as is the cosine of 2 pi. So, theta equals 2k pi. When k is equal to 0, theta is equal to 0. So the 0 of our function occurs at the point 0, 0. Now we want to find the maximum value of the equation. Our equation is in terms of cosine, and the value of cosine theta is always greater than or equal to -1 and less than or equal to 1. In our example, cosine has a negative coefficient. So the largest value of the function will come when cosine theta is equal to -1, or when theta equals pi plus 2k pi. Therefore, our largest value of r occurs when theta equals pi. This only gives us the second coordinate of the point. To find the first coordinate, substitute pi into our original equation and solve. So the maximum value of the equation is at the point 8, pi. Now we'll graph the equation. When we found the zeros and maximum value of r, we only found 2 points. We'll need a few more points to determine the general size of the cardioid. If we look at the polar grid, there are lines at theta equals pi over 4, theta equals pi over 2, and theta equals 3 pi over 4. Find the r values associated with each of these values of theta. Create a table with these values and then plot the points on the graph. The first point is at the pole 0, 0. The additional points we calculated are at pi over 4, 1.17, pi over 2, 4, and 3 pi over 4, 6.83. The final point is the maximum value of r at pi, 8. If we draw a smooth curve through these points and then reflect that curve across the polar axes, we get this graph of the cardioid.